Hello, chemistry students. Welcome. Here we are. We're going to be back looking at Big Idea 2. I just want to give you some example problems that I think could help to kind of pull some of these ideas together within Big Idea 2. So, as you can tell, I have a cold. I don't sound so good, but I'm okay. I feel good. Thanks for caring. All right, let's just go ahead and just kind of start by looking at some molecules right here. So let's say I have CO2, right? And let's say I have O2. And let's say that I told you the boiling point of each of those. The boiling point of CO2 is negative 70.6 degrees, so clearly a gas at room temperature. Oxygen, also a gas at room temperature, but its boiling point is negative 297.3. Whoa! All right, so this is an incredible difference. So what if you were asked to explain why this has a boiling point of negative 70 and why this has a boiling point of negative 297? What would you say? Well, first of all, if you're going to look at the structure here, first of all, you want to identify when we have polar, nonpolar. Okay, so anything that's going to be gas at room temperature, for the most part, you can be mostly sure that it's going to be a nonpolar covalent. So both of these are nonpolar covalents, all right? CO2, right, has this structure right here, and O2 has this structure right here, okay? So, so what is the deal? So why such a drastic difference? Well, a couple of things. When you're looking at O2, right? O2, it's just oxygens with each other, okay? So oxygens are very relatively small atoms, and they pull, of course, totally equal, right, to each other. And so there's going to be a lot more equality of sharing of electrons, plus this particular thing, the electrons that it's sharing are going to be a lot closer together. And now why does that matter? Well, the thing that would affect this boiling is going to be actually the only thing. It could be London dispersion forces. So London dispersion forces are going to be dependent on the random movement, right? The random movement of the electrons around these oxygen atoms. And so these London dispersion forces are occasionally going to cause a shift where this will be polar. Well, since this thing is so small, right, there's not a lot of distance for these things to move around. So, you know, an electron isn't really going to get caught too far away from another electron. So the London dispersion forces in this are going to keep this thing in the gas state. They're going to keep this thing from being attracted to any other oxygen molecules. Therefore, pretty much always a gas. I mean, you can imagine very few places are going to be, or situations are going to be that cold. CO2, on the other hand, you can see that we've got the carbon in the middle and the oxygen's way out here on the outside. Well, what is that doing? Well, it's actually just spreading out the electrons, you see. And so spreading out the electrons actually causes the ability for a brief ionic character to happen more often, to the tune of this much of a difference. And so what's going to happen is that CO2 will, because of London dispersion forces, will occasionally assume an ionic character, and so the CO2s will connect to each other as long as you get colder than negative 70.6. Another thing too is you do have this carbon in here, and so the carbon is going to disrupt the perfectly equal sharing of electrons right here. So that hopefully kind of gives you an idea of that. Now let's look at a couple other compounds. In the halogens often connect to each other, like I2, right? Because they've got 7 valence electrons, and so they say, okay, look at this. I've got 7, you've got 7, so we're going to get together and share. All right. So there's this really neat sharing that goes on. So here's iodine, right? And here's chlorine. They look identical, right? So they're just like this. We got all the dots. Make those dots a little faster. And so their structures are essentially identical. But when you look at When you look at the boiling points of these, the boiling point of chlorine is negative 34.04 degrees Celsius. So at room temperature, chlorine, diatomic chlorine, is a gas, right? If you look at the boiling point of iodine, it actually has to get up to 184.3 degrees Celsius for iodine to boil or to turn into a gas. Now this is one of those situations I was saying, most of the time you can be assured that these gases at room temperature are your polar, non-polar covalent bonds. Well, here's a non-polar covalent bond. Iodine isn't going to pull any harder on the electrons than iodine, so there's not going to be any reason for these to stick to each other. Yet at room temperature, iodine is actually a solid. And so what is that? Why is that a solid? And then this kind of obeys the rules that we've talked about. It's non-polar. They're not going to want to stick to each other, so at room temperature, they're a gas. Well, what's the deal with this? Actually, the deal is this. When you look at the iodine atom on the periodic table, you find that iodine is way down there. Iodine is a huge atom. In fact, this is probably the largest bond length of any molecular compound. These things are just hanging on to each other by this super long connection. And so what does that do? Well, it gives this enormous distance for these electrons to travel around while sharing through here. Well, because of such a huge distance, the distribution of electrons, maybe to one side more than the other side, is really common. In fact, it's so common that they actually assume an ionic character because of London dispersion forces, and a really strong ionic character because this is going to be solid at room temperature. And so iodine is one of these kind of anomalies, but the whole reason for it is because it's such a huge atom that these electrons have far more of a chance of shifting in a direction that creates one end negative and one end positive, giving it a strong ionic character even though it's covalent nonpolar. And this one right here, chlorine, is a relatively small atom. And so these ones are sharing in a very close proximity. So the London dispersion forces aren't going to cause this to be connecting to the other one because there's not much distance. And so it's not going to have a negative and positive end happen very often. So hopefully that helps to try to explain some of those. In the next video, I'm going to look a little bit more at bond lengths and bond strengths for you. And so I wanted to give you these examples because I felt like these were kind of confusing ideas, but I hope this helps.